All right, now we're going to look at comparing power functions with exponential functions. All right, and there's a couple different results here. One is for positive increasing exponential functions, and the other one is for positive decreasing exponential functions. So let's look at exponential growth first. So if we have exponential growth, which means that the function is a positive increasing function, then if you compare any exponential with any power function, the exponential always wins, okay? In the long run, it's always going to be greater than the power function in the long run. So exponentials dominate power functions always, all right? So here they're comparing 2 to the x and x to the fourth, and you can see that those cross each other, and x and 2 to the x grows faster than x to the fourth after some point. But even something like 1.005 to the x, which is pretty darn close to 1, it's not going to grow very fast at first, but in the long run, it grows way faster than x to the fourth. It takes a little longer for it to get there, but it grows faster in the long run. All right. So that's the first important thing to know about exponential functions, is they always dominate power functions in the long run. All right. So now let's look at the other, at the positive decreasing in exponential functions. So we have exponential decay. And so if you compare a positive decreasing exponential function with a power function that is also positive and decreasing. So here they're comparing x to the minus 2 and x to the 0.5x. All right, so power functions dominate exponential functions, right? So exponential functions are going to zero faster than the power function that's also decreasing, positive and decreasing. All right. So let's take a look at example 2. Now, I feel like example 2 is getting a little bit into dangerous territory, just because to predict the long run behavior of these functions, we really need something called L'Hopital's rule, which if you take Calc 2, you'll learn L'Hopital's rule. But we're just going to use what we know about the way exponentials and power functions compare in order to look at these functions, which are ratios of two functions, not necessarily rational functions because they're not two polynomials, but we're going to look at this ratio and see what happens in the long run. So we're going to predict the long run behavior of these functions. So let's take a look at this first one. Let's look at remember with long run behavior, we have to look at what happens as x goes to infinity and what happens to x as it goes to minus infinity. So in the first case, we've got 2 to the x over x squared. And we know that 2 to the x grows faster. 2 to the x grows faster than x squared, or really any power function in the long run. Okay, grows faster than any power function. And so what happens, just the same way that if we had x to the 100 over x squared, right? What would happen? We'd have x to the 98, and as x goes to infinity, it would go to infinity, right? So this, we're just going to predict that the limit as x goes to positive infinity of this f of x function is equal to infinity. Okay. So now let's look at the other way around as x goes to negative infinity. Okay. So now we're with the x squared is going to dominate in the long run, right? So the denominator is going to be bigger than the numerator, given what the result we had before. So and we also know that 2 to the x goes to 0, right? Because the x is negative, so this is would be the same as, you know, like 1/2 to the 1/2 to the x if x was positive, right? So that x to the x is going to go to 0, and but the two the um, the x squared dominates the the exponential function, so the limit as x goes to infinity of f of x is going to be 0. All right, because we're taking 0 and dividing by some larger number, and it's going to be 0, right? So it's going to be 0. All right. Okay, so let's look at the other way around. This is the same fraction, the same ratio, just flipped over. So let's first of all look at as x goes to infinity. All right. So now we know that 2 to the x grows faster. Right? We said that before. 2 to the x grows faster than x squared. So you could kind of think of this as that, you know, this function, if we looked at x squared over x to the 100, right, we'd end up with 1 over x to the 98, right? And that would go to 0, right? And by the same reasoning, we can say that the limit as x goes to infinity of g of x, right, is going to go to 0. Okay? Because this 2 to the x is going to grow a lot faster than even x to the 98 or x to 100, right? So, so we're taking, I mean, x squared is growing, but it's not growing as fast as 2 to the x, and so you're taking a larger number, or sorry, a smaller number divided by a larger number is going to become smaller and smaller. All right, so all right, now let's look at as x goes to minus infinity. This is where it gets really dangerous, right? And I feel like I'm kind of jumping the gun here. If you take Calc 2, you'll learn L'Hopital's rule, and you'll get a little better rigorous way of showing what these limits go to. But so as x goes to minus infinity, let's think about what's happening. X squared is going to infinity, and 2 to the x, right? So we're taking something negative and we're squaring it, but it's something big. We square something negative, we're going to get positive, right? And so that's why x squared is going to positive infinity. Now 2 to the x is going to 0, right? Because we're taking 2 to a negative exponent. All right, so that's going to go to 0. So it's a little bit tricky. Okay, we got infinity times 0. What is happening here? All right, now I could rewrite this. I could rewrite this function as x squared times 2 to the minus x, right? And then 2 to the minus x, when x is negative, is going to go to infinity. So it looks like infinity times infinity. All right, so we had infinity divided by 0. Now it kind of looks like infinity times infinity. So probably it's going to go to infinity. So, but again, like I said, this is getting into dangerous territory here. Like, getting way ahead of myself. So as x goes to minus infinity, and I just asked for a prediction, right? I would probably predict that g of x is going to go to infinity when x goes to minus infinity. But again, like I said, this problem is a little dangerous. So I'll leave it at that, and I'll meet you for the very last example of this chapter in the next video.